Hello, so this is equilibrium and the Chatalier principle, which is all about equilibrium. So what is an equilibrium? Before we can talk about that, we need to go over a few other things first. So, usually in a reaction, for example, 2 magnesium and an oxygen goes to 2 magnesium oxide. 99% of the time, you'll see just one arrow pointing in one direction. And that means we go from here to here, okay? So the reaction goes to completion. If I leave this long enough, if I look in 1,000 years' time, I won't find any of this because it'll all have changed into this, okay? This isn't the only type of reaction we can get. We can also get reversible reactions. Now, the main reversible reaction you'll need to know is the Haber process, which is N2 plus 3H2 goes to 2NH3. This is ammonia. It's called the Haber process used to make ammonia. And basically, not only can these gases react to make that gas, but this can react backwards to make those gases. So this is the symbol for reversible reaction. And what's actually happening, it's not like we just have these gases sat still on their own, and we just have ammonia sat still on its own, so the concentrations remain the same. Every second, thousands of these are breaking apart back into them. But thousands of these are reforming back into that. So we've got backwards and forwards reactions happening at the same time. Now, when the backwards reaction equals the forwards reaction, we say we've got an equilibrium, okay? The concentrations will remain the same. Now, in a proper equilibrium, where the concentrations remain the same, the position of equilibrium is in the middle, okay? That means that for every molecule change into that side, you've got a molecule change into that side. But what we can do, using certain conditions, is we can change the position of equilibrium. So for example, rather than it being in the middle, so equal products and equal reactants being made, I can change the position of equilibrium to the right, so over here. That means the forwards reaction is happening more than the backwards reaction. So the concentrations on this side will decrease, and the concentration on this side will increase. And just like that, I can also shift it to the left, over here, so that means this concentration will increase and that concentration will decrease. So basically, we can set up an equilibrium, or also called a dynamic equilibrium, where molecules are being constantly, basically cycled around, and we can have a position of equilibrium either in the middle, where it's all equal, or to the left or to the right, and that basically just shows us which direction is happening the faster, if that's a word. Okay. So, as previously mentioned, there's a few different conditions we can use to shift this position of equilibrium. With that reaction there, nitrogen gas and hydrogen gas aren't very useful to us, or certainly not as useful as ammonia, which we use as fertilizer. So what we want to do is shift that equilibrium to the right hand side to get more ammonia. So let's look at a few ways we can do that. We've actually got pressure. We can use pressure to shift the equilibrium to one side. We've also got concentration. We've also got temperature. And I'm going to talk about catalysts right at the end, okay? Now, all this shifting of positions of equilibrium to make one reaction happen faster than the other, this is basically called the Chatalier principle, because it was formulated by a dude called the Chatalier. And he said this: if a system in dynamic equilibrium is subjected to a change, it will shift the position of equilibrium to minimize that change. So for example, if I increase the pressure of my system, then the position of equilibrium will change to reduce the pressure. If I increase the concentration, it'll change to reduce it, and same with temperature. So let's look at pressure, okay? Throughout all of these, all I want you to think about is this sentence, or this paragraph, okay? So pressure. Let's go back to my equation. So for all of these, I'm going to use the Haber process as my example, because that's the one basically you need to know the most. If I look at the number of gas moles on each side, I've got 1 mole here, I've got 3 moles of gas there, so that's a total of 4. But on this side, I've only got 2 moles of gas. Now pressure is caused by gas atoms hitting the side of things. That's why when you blow into a balloon, it expands. Because as you blow in, you increase the number of moles of air inside, and that pressure increases and expands the balloon. Okay? So, if I want to increase the pressure, all I need to do is increase the number of moles of gas molecules. If I want to decrease the pressure, all I need to do is decrease the number of moles of gas molecules. Okay? So, think back to this. It's always going to try and minimize the change. So let's say I increase the pressure. I put loads of pressure on my system. By shifting the position of equilibrium, I can reduce the pressure. So it starts off in the middle. If I increase the pressure, in order to reduce it, my position is going to shift to the right-hand side, because that will reduce the number of moles of gas and therefore reduce the pressure. So basically, if I increase the pressure, the position of equilibrium will move to the side with the least moles of gas. Not moles of everything, doesn't matter about solids, doesn't matter about liquids, the least moles of gas. If I decrease the pressure, in order to minimize that, my position would shift to the left-hand side. So I increase the moles of gas. Okay? So it always does basically the opposite of what you're doing. And that's pressure. Concentration is exactly the same. So let's say, well, I'll use the same one again. So you've got my Haber process. Let's say I increase the concentration of this side. So I put loads and loads of nitrogen gas in and loads of hydrogen gas in. My equilibrium, my dynamic equilibrium, will shift the position of equilibrium to reduce these concentrations, because it always tries to minimize the change you've made. So if I increase this side in concentration, the position of equilibrium will shift to this side. So I'll make more of these into that, which makes sense when you think about it. If I add more of that, of course it's going to make more of this. Okay? Let's say I increase the concentration of ammonia. The position of equilibrium, in order to decrease this concentration, would shift to this side, to the left. So more ammonia is being changed into my gases. So it always does the opposite of what you're doing. Okay? And we've also got temperature. Don't know why I wrote that out again. Okay, basically this is an exothermic reaction. So this side gives out heat, whereas this side is an endothermic reaction. So it takes in heat. Okay, if I took it, it's fine.
Sorry, I didn't know you.
No, it's okay, it's fine, don't matter. So this side, this reaction, the forward reaction, gives out heat energy. So that will increase the temperature of the surroundings. Yeah? Exothermic reactions increase the temperature of the surroundings because my chemicals are given heat energy to the surroundings. Endothermic reactions, so the backwards reaction, will suck up heat energy from the surroundings and decrease the temperature. So, if I was to increase the temperature, in order to minimize that change, so in order to reduce the temperature, my position of equilibrium will shift in the direction of the endothermic reaction, like that. So it sucks up heat and reduces the change. If I decrease the temperature, if I make it colder, then my position of equilibrium will shift in that direction, the exothermic reaction, to give out energy and minimize my change. So it's always trying to do the opposite of what you're doing. And very, very finally, catalysts. Catalysts have no effect on the position of equilibrium. So if you ever get asked about catalysts and equilibrium, you can just say they don't do it, and that's the Chatalier principle.